Hello everyone, my name is Sebastian Böcker. If you see this talk out of context, we are the people behind Sirius, CSI, Finger ID and so on. But this talk is about a different subject. It's about metascores, why we don't use them in our tools, and why we don't think it's a good idea that anybody is using them. I must say that I'm not particularly keen on recording this talk. A few years ago, I've written an opinion paper, and in this opinion paper, there are already several of the ideas which I will also discuss here in more detail. I hope that after that somehow people would understand that using metascores comes with a lot of issues and people would not do that, but that turned out to be wrong, and this is why I now record this talk. So as usually in my talks, I'll do a very short intro where we are. We are doing untargeted metabolomics or something very similar. So we are looking at small molecules inside some biosample, and we are using LC-MS and tandem-MS, MS-MS to find out what is in there. And for that, we want to use an in silico method because we assume that library search can annotate only a fraction of the compounds in our sample, and we are not happy with that. We want to annotate more. Then a metascore could in principle be any type of score that somehow combines different types of information. But in the context that I'm talking about, this is always the same type of metascore. It includes information that is from the structure database we are searching in. And such information might be the production volume of a particular compound, the number of citations of a particular compound, and so on and so on. And we now modify our search results based on this information. Now in the following, we will concentrate on one type of information simply because it's easier. I don't want to repeat myself, and that is the number of citations. Everything also goes through for the other types of information. Now a word of warning, highly cited, what does that mean? Keep in mind there's always a bigger fish, but if the pond is small enough, then already a very small fish can be pretty large. What does that mean? You just compare as a candidate molecular structure against other molecular structures which are candidates for an in silico method. And if you have more citations than the other candidates, then you are highly cited. And what are those candidates? Candidates are chosen by the in silico methods based on the precursor mass or maybe the molecular formula of the compound. So if you have a lot of citations, more than the other ones in this pool, then you are highly cited. Now, I already mentioned that our tools, in particular CSI Finger ID, which is for searching in such a molecular structure database, are not using metascores. Why is that? Are we maybe too dumb to use them? Or is there another reason? Spoiler, there is another reason. In fact, there are 6. And the short answer to this question is that there is no free lunch. You will have to pay one way or the other. And for the long answer, watch this talk. One thing that I've noticed discussing this subject with other people is there appears to be some misunderstanding because metascore sounds a little bit like metadata. But you have to understand that metascores have nothing to do with metadata. So what is metadata? Metadata is data about your data. It's information about your experiment. It's information about your mass spectrometry, such as the mass accuracy or the ion mode, instrument type, and so on. It's information about your liquid chromatography, assuming that you're doing LC-MS or LC-MS-MS. But it's also information about your sample, such as the organism you are looking at. There are numerous standards of recording that, and I really believe this is very helpful information and you should record it. It also helps a lot for reusing your data at a later stage, be it through us, be it through MUST that uses the organism, so you don't know that a spectrum is this or that compound, but you at least know that it's frequently found in mice. So definitely helpful, and actually we already use it. Many in silico methods use it. For example, mass accuracy. We all use the mass accuracy. We use the ion type. We have different machine learning models for positive and negative ion mode. So yes, this is good. But metascores do not use metadata. They use different types of information. And this is information that comes from the molecular structure database. And this has nothing to do with your experiment. It simply assumes that a compound that is, for example, often cited is more likely to be present in your experiment without knowing anything about your experiment. Okay? So what it boils down to, and we'll get back to that example, is any molecular structure with this molecular formula always cocaine. I'm assuming that cocaine is the most cited compound. I didn't actually check it, but as a Gedanken experiment, accept that this is the most highly cited compound, and now you find tandem MS here. And is it automatically cocaine just because this is the most highly cited compound? Because as we will see, this is going to happen with most metascores. So what are the problems with metascores? For me, the biggest problem is that the longer I think about it, the more problems I find. So I stopped thinking about it and I thought I now record this talk, and then I don't actually have to redo everything in a few weeks when I find the next problem. The first problem I want to discuss are blockbuster metabolites. Let's assume we want to do something very different. Let's assume we want to build a movie recommendation system. Everybody knows movie recommendation systems these days because as soon as you start Netflix or YouTube or Disney Plus or whatever, you actually run into such a movie recommendation system. And that tells you, oh, people that like the movie that you've just watched also like the following movies. And yeah, that's actually a part of artificial intelligence, not machine learning. It's older than that. It's a little bit different. But let's assume we have made such a system that learned that from the tons of data we generated with our app. And now somebody has a very smart idea. Somebody comes along and says, let's also put in the gross of the films. How much money did we make with some films? Okay, there are such lists. You can download them. Wikipedia has them, and they tell you what are the highest grossing films on Earth. And now a high grossing film should be more likely that somebody wants to watch it than a film that made relatively little money and so few people are interested in it. So let's combine that. What's going to happen? Now we have built a system and we can enter something in our search bar, and let's see what the system then recommends to us, and voila, here are the search results. And that seems to make some sense. Okay, we put in here animated movies and we get some animated movies back, and then people who like Disney movies probably also like movies from the Marvel universe. That's why they are also available on Disney Plus. Or what about Star Wars movies? Oh, they are also available on Disney Plus. So that appears to make some sense, right? Then let's try something different. Let's be a little bit more arty. What do we get now? Okay, that's funny. Okay. Yeah, why not? We put in some Hollywood movies, even though they are a little bit more arty. It's nevertheless Hollywood movies, and we get a lot of Hollywood movies back. So that makes some sense. Let's go horror then. How about this Shining Rosemary's Baby Eraserhead? What do we get back? Oh, you might already guess what we are getting back, because we will always get back the same stuff. Because we simply assumed too much that a high grossing film is of more interest, even if those films make 10, 100, 1,000 times more money than, say, Eraserhead. Yeah, somebody who has seen Shining and Rosemary's Baby doesn't want to see an Avatar or Titanic next. They are more interested in Eraserhead. But our Metascore, which we just built, makes it completely impossible to ever find that. The only thing we can find now are blockbusters. This is what we are going to get, and this is what we are going to get all the time, because they are so high grossing that no other film can ever overtake them, no matter what you're interested in. So what we have built is now a recommendation system, which is working, I have to say, because it's recommending for many people movies which they really like. But I don't think it's a particularly helpful recommendation system. Probably without adding in this information, it would have been more helpful. it might have not recommended so often the blockbuster movies, which then would, somehow made it worse in evaluations, and we'll come back to that in a second. But I think the recommendations would have been more helpful. Now, if we use a metascore in an in silico method, we do exactly the same. We only return blockbuster metabolites. Those metabolites that have loads of citations will simply turn up at the top position of our search results almost always. It depends a little bit how we now weight the metascore, like how much do we think is the MS important and how much is the citation frequency important. But in principle, this is going to happen. We only see blockbuster metabolites from now on. And this information was, for example, in the MedFrag2 paper. And they clearly said that this is going to happen, or at least this can happen, and you should be worried about it. But what I got, I get the feeling in the last years that nobody's really reading this. People are not noticing this. They are just using the metascores, and I'll come back to that, why they're using it, and they are not reading this warning. But there's another problem, and this problem is somehow independent, somehow connected to the blockbuster metabolites. It's independent that the blockbusters would be a problem even if we could get past this problem, and it's connected that, these blockbuster metabolites make a lot of trouble. And that is evaluations. If we evaluate such a metascore method that uses the metascore, we will see that they perform really, really good. But if they perform so well in evaluations, and that's even in blind competitions such as CASME, they perform so well, aren't we morally obliged to use them? Okay, how can I tell you not to use them? That's strange, that's crazy. Well, the problem lies in this chart. And that nicely explains why these metascores perform so well in evaluations, and why this has nothing to do with performance in real life. What I've shown here is the fraction of compounds in a database that have 0 citations, 1 to 10 citations, 11 to 100 citations. Remember, it's not important if it's citations, it's just one of the many things you can use here. It looks like that for any of those things. And you see that in PubChem, almost all of the compounds in here have 0 citations. Very few have 1 to 10 citations, and then you actually can't see if this is 0 or not. In fact, this is not 0 because on an absolute scale, these curves are subsets. These sets here are subsets of PubChem, but you only see that in these curves because the total number is much smaller. So this is the biostructures. It's a subset with 500,000 structures, which we combine from several biomolecule structured databases. So it's also molecules of biological interest, not just core biomolecules. And what you see here is they have many more citations than PubChem structures on average. So only 70-something% have now 0 citations. And this gets, also here there's a large increase now. Here's a large increase. But now if we look into spectral libraries, something funny can be seen, and that is those compounds have even more citations, okay? Loads of them have more than 100 citations, more than 1,000 citations, often even more than 10,000 citations. But why would we care? We are evaluating in silico methods here, and in silico methods do not search in spectral libraries, right? Wrong. They don't search in spectral libraries, but we evaluate them using spectral libraries because we need a data set where we know the ground truth. And that's usually a spectral library that you download from somewhere and then test how good your method works on that. And so we evaluate this using these blockbuster metabolites because that's mainly what is recorded in those spectral libraries, and that's because they contain commercial standards, and commercial standards are much more likely to be cited. Yeah, and if something is cited a lot, then it's more likely to become a commercial standard. So we evaluate our methods on blockbuster metabolites, and there's not the slightest chance that in reality when we also have non-blockbuster metabolites, our methods, our metascores, which perform as well. So in principle, what we are doing here is we have made an app for bird identification. And this app is a little bit stupid. It can only annotate penguins. And then we go to the South Pole to evaluate it. And it's saying penguin, penguin, penguin. And we are super happy because it's saying penguin all the time. And I would be really careful. And this is even worse because people do not only look at these independent or large-scale evaluations where people report statistics about how often the method is able to correctly annotate a compound. They also tend to do some small experiments and check whether an app method can actually annotate something useful for them. And I have the feeling that people then try out a method with, say, amino acids. And then maybe one of the amino acids is wrongly annotated. And people are like, wow, how good can this method be if it cannot annotate an amino acid? And the metascores, they will always get the amino acids correct. Because, I mean, yeah, amino acids have so many citations, obviously, they'll end up on the top no matter what the tandem MS is, as we will see later. So the logic seems to be if a method is not able to annotate amino acid, then what can you use it for? What can it be good for? But that doesn't make sense. It's actually the other way around. I mean, I can build you a method that will always annotate an amino acid, even if you put in something completely different. That will always annotate you something with a blockbuster metabolite. If you are happy with that, okay, it will also annotate the non-blockbuster metabolites as blockbuster metabolites. This will pass this test, but it's still a stupid method. It doesn't make sense, okay? You should be worried that a method can only annotate amino acids instead of saying, oh, it didn't annotate amino acids. In silico methods don't know that there's something special about amino acids. Why should they be capable of annotating amino acids all the time? Now, comparing a method without a metascore and a method with a metascore is like comparing apples and oranges. And in fact, I'm showing this bar chart here because the authors went one step further and actually also threw starfruit into this procedure because they compared a method that is not using any metascores plus an in silico method that is using a metascore plus library search with metascores, which is then actually aggravating all the problems that I talked about earlier. Okay, so stop doing that, stop comparing those numbers. It does not make any sense. But even worse, sometimes a metascore might obfuscate a good search result. What I mean here is that sometimes, yeah, your search results that you get, say we have a tandem MS and our in silico methods finds a few structures. I assume that the score is somewhere between 0 and 1000, and a few candidates get almost the same score. It's not a very high score. I'm not sure if this annotation is correct. And then you throw in such a metascore, and then this might be useful. You get the right candidate at the top position. And if you would have now to check with an independent method anyways, if this annotation is correct. So that might be helpful. But in a different example, we might have 3 other structures for a different tandem MS, and one of these structures really got a high score, and the others got, lousy scores, which you would assume also happens a lot by random chance. And that would now be a pretty good candidate for a correct annotation. I would like to check that. It might be correct. You should check that definitely. But now you throw in a metascore, and unfortunately this guy got very few citations, whereas the other ones got really loads and loads of citations. And now what happens is that not only is this flipped now, but also you see as the top candidate now, as the annotation of the method, a blockbuster metabolite. And if you see that and only look at this search result now, you will probably say that this is pretty boring and you'll not go into it. You will not go after the structure D anymore because this is a boring search result. the blockbuster metabolite is probably in your sample, so it annotated that. That's boring. Forget about it. So this is statistically happening all the time, and you're not going to notice it. You are losing good search results. So why am I worried about this problem? Why do I worry you? Because I believe there's a lot of compounds out there which are actually novel, and we haven't seen them at all so far. And these are just 3 examples where we and other authors found novel bile acid conjugates, which at that time, I have to say, were not even in the structure databases. But assume they were in the structure databases, they would have had 0 citations. Nobody has ever seen them in real life, and nobody would report them in a paper. Okay, so those would have been out. You would have missed interesting compounds, possibly even novel compounds, because you rather went for the blockbusters. And I don't think this is a good idea. For the next problem, I have a trick question for you, and that is, why do we record tandem MS anyways? Why do you go through all of this hassle? It's a lot of work, if I understand that correctly. And do you really have to do that? And the problem we are facing here is really nicely described in the MedFrag relaunched paper from 2016. There's a very nice table in there, and it explains everything, but I just have the feeling that not many people ever looked into this table and understood why this is a problem. So what is the problem? The authors nicely analyzed or evaluated how many correct annotations they can reach if they put in different types of information. So if they threw in the MS1, which is the precursor mass, and the tandem MS, they got 30 compounds correctly annotated from their set. Okay, and now they use different types of information. Now they use the precursor mass and the number of citations. And it goes up to 311 correct annotations. Oh my God, that's more than tenfold the number of correct annotations. And the point here is they are not using tandem MS at this point. It's not needed. They went one step further and checked how many compounds they get correctly annotated if they use all of the information, so precursor, number of citations, tandem MS, and they get a few more, 322. But the difference between those two is not really big. 96.5% of the performance can be reached if we just do precursor mass plus number of citations. We only get this really low number. Okay, that's 3.5% or 2.3 percentage points. We only get this super small number through adding the tandem MS data in there. And now my question to you is that worth the hassle? So we see that the performance of our method is basically the same whether or not we are recording tandem MS. And as I have already said, then let's not record them. We don't need them. It works without them, correct? It's so much hassle to record them. You can run much faster gradients. Maybe you don't even need all the liquid chromatography part. I mean, you can read something by Nicola Zamboni. I think he's not using them. He's just recording the MS1, and that's enough. And actually, there was a paper proposing that by Little et al. Many years before people were using metascores. So, if you think that this is okay in your untargeted metabolomics experiment to use just the MS1 data to annotate metabolites, then go for it. Use a metascore. Actually, you can leave out the MS. It's not needed. Just use the metascore. But if you think that there's something wrong, something is terribly wrong here, do not use metascores. Now, the next problem is that metascores have a tendency to blur where you're actually searching. People report that they are searching in PubChem. And that sounds like a really huge database. But I already indicated that this is not really true. If you look at all of PubChem, it's, as I said, it's hundreds of millions of structures, or at least 100 million structures. So that seems to be, wow, that's incredible, much larger than a spectral library. But by using a metascore, you actually gray out 99.9% of this database. It's impossible that it's ever be found, because for any precursor mass you can possibly look at, you will find compounds which then have more citations than your compounds with 0 citations. If you're lucky, then nothing has a citation for a particular precursor mass, so such a method might then return also something that has no citations, but usually you don't see them anymore. They are not there. They are hidden. And that's really nasty. We are not now searching in PubChem. Oh no, we are not searching in PubChem. We are searching in a subset of PubChem. We can't really tell you what the subset is. It is somehow connected to citations. I mean, then even the spectral library becomes much more untargeted, right? And that's now really strange. People use these in silico methods, or at least that's what I heard a lot, to overcome the limitations of spectral libraries. Okay, spectral libraries are very nice if you have spectra available, but very often you don't have spectra available. What do you do now? And now an in silico method can overcome that. And now we restrict ourselves even further than with such a spectral library, because a spectral library at least doesn't introduce a upfront score on certain spectra are more likely to be present in your sample than others. It simply says, is the spectrum similar or not? Okay, that makes a lot of sense. That's not what a metascore is doing. A metascore, even in those cases, would then say, oh no, this compound is already 10,000 times more likely than this compound. So the last problem I want to talk about is overfitting, something people in machine learning are very well aware of, that this is always a problem. And this is about the reasoning that we have used citations in our metascore and it improved our annotations. So this makes sense because obviously citations is a good feature to use for that, right? It's an input feature. Machine learners talk about features. It makes a lot of sense. So that's why the performance is good, right? Well. We propose a new method. It's Mad Hatter. It's from Alice in Wonderland. You might know him. These beautiful drawings are by Sir John Tenniel. And it's also using a metascore. And besides the CSI finger ID score, it will use additional information. And I'm showing the information here. So this all makes sense, right? So it will perform very well in evaluations, right? No, that doesn't make sense. So why should it? Oops. It works. The point is, it doesn't matter if the information that you put in there makes sense or not. Okay? Just because you see that it works in practice does not mean that you are actually doing something that makes any sense. Machine learning will pick up a lot of hidden things that you're not aware of, and you should be super careful. This is just an intermediate result. I hope that we can push Mad Hatter to 90% correct annotations. I really hope that. And you shouldn't follow the logic that just because it's working in evaluation means that it makes any sense to do it. So be very careful. If you think that Mad Hatter doesn't make sense, and actually does not make sense, and I don't think anybody should ever use it. But if you agree with that, then you should treat metascore search results with extreme care. So these are the 6 problems. I'm not going to repeat them, but just so that you can see them on one slide. And now I have told you all about these problems now with metascores. Is there anything positive that I can say. My first suggestion would be you can use background knowledge, and for me, citations, number of citations of a compound or a structure are background knowledge. You can use that, but please use it yourself. In fact, I believe that you are the best person as a chemist, as a biochemist, as a biologist to include such background knowledge and think about it, rethink if it makes sense. But I ask you to do that after the in silico method has done its work. Then you can check, then you can see how many citations do these different compounds have. And then you can avoid doing harm. You should be aware you might do harm because, as I showed, this overfitting is going to happen anyways, even like when you are applying it. It might be that you lose an interesting annotation because you think, no, this other thing is 10,000 times more likely to be there. No, it was actually the unlikely thing. Bad for you. But you can really see for yourself how much harm you are causing and if you want to cause any harm, if you go after something. And you will definitely not say that this molecular formula is always cocaine. And in fact, we can also use the metascores into our in our in silico methods, and that was first done in Magma. Lars Ritter has done that, and they used it to resolve ties. They used citations to resolve ties. So if different annotations got exactly the same score, then they were displayed in an order according to their citations. And I was in the beginning not very positive about it, but now I think it was really, really a smart idea. So I have to excuse that I initially wasn't that enthusiastic about it. And that's more or less what we also do for CSI Finger ID now. We simply display the number of citations and you can check whether or not this is interesting information for you. The second suggestion is, why do you search in PubChem? I mean, with a Metascore, you're not searching in PubChem anyways, but why are you claiming to search in PubChem? I always show this slide when I talk about CSI Finger ID, and I always say this is a good database for evaluations because it's large. It really, really pushes the methods to their limit, and you really see the difference. But in applications, I always say search in a smaller database, one where you know it makes some sense to search in there. We, for example, by default search in a biomolecular structure database, which contains something between 500,000 and 1 million compounds depending on the version. I mean, earlier publications used smaller databases. The databases are growing because we are integrating more, and the databases like HMDB themselves get new versions. Or use an in-house database where you're pretty sure those are the interesting compounds. Or you might even use hypothetical structures. I don't care, but search there first. The important point is that it's very different from a Metascore because now all structures in the database are treated equal. So we don't say this structure without even knowing the data, without even knowing the sample is 100 times more likely than this structure simply because it has more citations. Okay, they are all the same. And you can now report where you have searched. It makes a lot of sense. You can now say that you searched on this or that database. And it's not that bad. I mean, I have to say that the CASME 2016 data is really excellent data, and it's really the top performance you should expect from a tool or from any tools. But CSI Finger ID reached on that data 74% correct annotations when you search in a reasonable database, which is a database with biomolecular structures, 500,000 structures. But then we might lose something. What about those compounds which are currently not in that database? Well, you can search in PubChem, but you shouldn't do it in the first step. What I suggest is you first look at the search results in your restricted database, which can be the in-house structure database, or it can be all biomolecular structures or something like that. Then you check whether you believe this annotation already, and you only go to the larger database in case you find really nothing interesting in your restricted database. So in the first case, we searched in the restricted database and we find something that really looks good. Again, scores between 0 and 1000, so 870. That's probably correct annotation. I'll come back to that in a second. Does not necessarily mean that, but let's assume it would mean that, then there would be no need for a second round. Whereas in this case, we also found only one structure in the small database and it has an average score. So I would definitely look into the larger database and check that in there if there are other structures which are now more highly cited. I mean, 21 is also not really highly cited, but if I would go through them and really now use an independent method to check which of these annotations is actually correct, you might actually start with structure C. That's absolutely no, I have no problem with that. But now the interesting part comes, and that is we search in our biomolecular structure database, again, not just biomolecules in the restricted sense, but also molecules of biological interest, and we find nothing. Actually, the candidate list might be completely empty. And for those MSMS, it makes a lot of sense to search in a larger database, all of PubChem or something in between. Like if you started with your very restricted in-house database, you might now search in a biomolecular structure database. And then suddenly you find something in there which gets a really good score and the other ones, get bad scores. Then this is interesting, even if it doesn't have many citations. And as I said, if you search in PubChem, almost nothing will get a lot of citations. The problem is that not necessarily does a high score of an in silico tool tell us that this is a correct annotation. It's really hard just from these scores to tell which of these annotations is correct or incorrect. What we really needed was something that told us if we should have confidence in this hit, yes or no, or this hit or this hit. If only we had a method that could do that. So the bad news is that you cannot use the scores of an in silico tools to decide whether or not an annotation is correct. So what I just showed you was misleading. It's okay for spectral library search where something close to 1 is then usually also corrected, but it's not at all true for those in silico tools where I actually used the scores from a CASMI contest. So that wasn't even run by me. And what you see here is that at any reasonable FDR, those methods, those scores don't return you a large number of hits, and that actually means that the scoring is more or less random by these scores. So what we really still need is a method to assign such confidence. When is a hit correct? And obviously we already have such a method, and that is called COSMIC, or more precisely, it's the confidence score of COSMIC. And I'm not going to repeat that here. Just watch the talks that I provided for COSMIC and the confidence score. But what I want to say here is that this confidence score now helps enormously as part of such a multi-step approach. So first we search in a very restricted database, and then we let the confidence score decide which of those annotations are probably or more likely to be correct. And then we take those that have a low confidence and research them in a larger structure database. And again, we can assign confidence to that, and so on and so on. And with that, we come to an end. Many thanks for watching this. I hope that I raised at least some concern about using those meta scores and why you should be very careful and why you shouldn't think that you are actually now using a method that is good in annotating structures, and why it's not a good sign that you get all your amino acids assigned in the first tests, and so on and so on. Yeah, what else can I say? I think nothing. I really hope that I got my message over and that I don't find problems 7, 8, and 9 in the next 5 days, so I don't have to record this talk again. So have fun, take care, and bye.